Hello ladies and gentlemen, welcome to my talk about north finding with a single double mass MEMS gyroscope. We chose the north finder because it is a very good example to demonstrate the precision and stability of our in-house developed MEMS gyroscope. In the beginning, I want to thank my co-authors for their support and the committee for the opportunity to present this work. Let's get started. First, I will talk about our motivation. Why do we want to use gyroscopes in north finding devices? Then I want to introduce to you the two methods which are commonly used, the carouseling method and the Maytaging method. I want to discuss advantages and disadvantages in order to explain our choice of method. Next, I talk about the sensor we use in our north finder, because as I told you before, it was developed by our partners and us. I introduce you to our MEMS fabrication technology and show you how we can improve the performance of the gyroscope even further via quadrature compensation. Last but not least, I show you the complete system and explain how it works. So why do we want to use gyroscopes for north finding? The most popular method is to use a magnetic compass. However, depending on your surroundings, it will point you in the wrong direction. This is caused by local disturbances in the Earth magnetic field due to magnetic material near the compass. Especially in buildings made from reinforced concrete or next to magnetic metal objects or even underground next to ferrous minerals, magnetic compasses cannot be used for orientation. Also, the magnetic north pole moves over time, which makes it not a stable fixed point. GPS could be used for orientation, but it requires an electromagnetic satellite signal, which cannot be received everywhere. Needing at least two receivers with a certain distance from each other, depending on the GPS resolution, it also consumes space for accurate orientation determination. With gyroscopes, the north finding relies on the precise measurement of the Earth's rotational rate and its orientation with regard to the sensitive sensor axis. If we change the sensor alignment with respect to the Earth's rotational axis, we modulate the measured signal. Like a compass, an easy way is to rotate the sensor axis in a plane parallel to the surface of the Earth as shown in the lower figures. This results in a modulated signal following a cosine function with maximum in north and minimum in south direction, respectively. The biggest amplitude can be measured on the equator, which is the Earth's rotational rate of 15 degrees per hour. This is half as fast as the hour hand on your analog watch. Moving away from the equator, the amplitude of the signal decreases even more, as shown in the lower left sketch. For example, in my hometown Chemnitz, it is only 9.5 degrees per hour. The precision needed for north finding was only available through big, heavy, expensive mechanical or ring laser gyroscopes. However, MEMS gyroscopes nowadays reach a precision high enough for north finding's application, making it less expensive and portable. For the carouseling method, the sensor axis is rotating continuously and the signal is measured during the rotation. The resulting signal is shown on the right side. You can see the cosine behavior of the signal as explained on the previous slide. An advantage of this method is that one can evaluate phase and amplitude of the signal using a log-in amplifier. Therefore, slow signal drifts, for example due to temperature changes, are factored out. Also, the method allows a continuous evaluation of the signal, causing very small measurement delays. However, a disadvantage is the vibration of the rotational drive, which disturbs the very small measurement signal to a point where it makes it impossible to extract the signal. Laboratory rate tables are able to rotate the sensor with very small vibration, but are often very heavy, not mobile and expensive. Also, additional force components like centrifugal forces will influence the vibrating mass of the sensor and therefore change the measured rate value depending on rotation, speed and alignment. The second method is the so-called Maytaging method. Here the measurements are done for discrete orientations in between the rotation. This keeps the measurement signal for the specific orientation constant as indicated on the right side. An obvious advantage is, compared to the carouseling method without rotation during the measurement, no vibration disturbs the sensor. Also, no additional dynamic forces act on the sensor. As the measurement signal is constant for each orientation, the measured values can be averaged as shown with the black dots in the figure. This decreases the amount of data to be evaluated and enables a check for other mechanical disturbances during the measurement, as the standard deviation of this point would be higher than normal. Because of this, the point could be discarded or even remeasured. The measured values with their corresponding orientations can be fitted and the phase be extracted. On the animation, you can see that the starting orientation can be varied, and the phase is always unambiguously determined. As the fit needs at least 2 points, the orientation value has lower update cycles compared to the carouseling method. Also, slow signal drifts will have a bigger effect on the determined phase and are harder to exclude. As mentioned before, the angular rate we want to measure is very small. And that is why now I want to show you our sensor and why it is suitable for this application. The angular rate sensor consists of a MEMS gyroscope and an ASIC for signal conversion in one small package. In order to reach high sensitivity, the MEMS is a tuning fork gyroscope with heavy moving masses. The detection is done by capacitance measurements, which benefit from the high aspect ratio of the trenches. In our case, the aspect ratio is around 30:1. The MEMS is manufactured using full silicon or glass silicon glass bonding and deep reactive ion etching, and this technology is constantly improved by our partners in the Center for Microtechnologies at the Technical University of Chemnitz. In the lower left, 2 examples of etched MEMS structures, namely drive and sense electrodes and their associated springs and attachment frames, are shown. The MEMS design is adjusted to the manufacturing process as well as to the electrical interface of the ASIC developed by our partners from Electronic Design Chemnitz to achieve maximum performance. In the package, the ASIC sits directly on top of the MEMS, which guarantees short electrical connections and needs less space as shown in the photo of the open package on the right. Around the MEMS ASIC stack, an interposer with some capacitors is placed. Here, 3 variants of the used Petri method are shown. All consist of 3 basic layers: a bottom wafer with cavities and supports, an active layer with the moving components and springs, and a top wafer with vias to contact the electrodes in the active layer. The glass silicon glass stack on the lower left has the advantage during development that one can look through the top layer directly on the moving structure. Inner metallic connections can be easily inserted on the insulating cap wafers and allow a flexible contact placement. The full silicon variants on the right, on the other hand, are less prone to stress in between the layers, as the base material is the same through the whole stack. An additional inner circuit layer can be inserted by using a structured silicon on insulator top wafer, making electrode placement flexible as well. The performance of the sensor can be measured by means of bias instability and angular random walk. Both parameters are extracted from the Allen plot, which shows the Allen deviation of a signal for varying averaging interval lengths called cluster time. Usually, longer cluster times decrease the error of a value, but due to long-term drifts in the signal, the error gets bigger again. The minimum error is called bias instability, indicated by the red line in the figure, and tells us the best resolution we can reach with the sensor. The angular random walk, shown as the green line in the figure, is a measure for white noise in the signal produced by the sensor. White noise can be averaged to enhance resolution, and therefore the angular random walk gives us a lower limit of which resolution can be obtained in which averaging time. The bias instability has to be lower than the signal you want to measure. In the example here, we reach an Allen deviation of 1 degree per hour at a cluster time of 5 seconds, which is 1 order of magnitude lower than our measurement signal of 9.5 degree per hour. To lower the angular random walk and bias instability values, unwanted signal components, one of which is called quadrature, have to be minimized or even removed. The quadrature is caused by the non-ideal movement of the sense electrodes in the direction of the drive excitation. There are 3 ways to exclude this contribution from the measurement signal. The first one uses the phase difference between the rate signal and quadrature signal and filters out the quadrature signal in the conversion electronics. The second method compensates the quadrature movement by applying an AC signal to the sense resonator in a closed loop, working against the quadrature movement. And the third method is to apply a DC voltage to special designed quadrature electrodes at the Coriolis frame, which results in a self-modulating force caused by the drive excitation. The latter one is used in our MEMS and shown on the right side. Here we see the Allen plot of a sensor before quadrature compensation. Without compensation, the quadrature of the sensor is approximately 210 degrees per hour. The angular random walk is already below 0.1 degree per root hour and the bias instability around 1 degree per hour. If we apply the DC voltage to the quadrature electrodes, we can remove the quadrature component. This results in a reduction of both angular random walk and bias instability values. The noise decreases about a factor of 5, whereas the bias instability decreases even more than 1 order of magnitude to below 0.1 degree per hour. The influence this has on the precision of the determined north direction will be discussed later in the talk. Now we have a look on the gyrokompass. It consists of two main parts, a fixed base and a free rotatable sensor compartment. The base, shown on the lower right side, contains the power supply and the stepper motor, a display for state monitoring and a microcontroller for motor and measurement control. In addition, the phase fitting is implemented in the microcontroller. Communication with the sensor part takes place via Bluetooth. The sensor part, shown on the upper right side, is powered by battery and consists of the gyroscope, a microcontroller for data collection and pre-processing, and the Bluetooth slave module. By the way, all used components other than the sensor are consumer-grade electronics. The measurement procedure is as follows. First, we choose a random starting position and set it to be the 0 degree position. Then we measure the rate in this orientation for a certain time. The data obtained with 5 kHz sample rate is averaged by the microcontroller in the sensor part. The averaged value is then sent to the base, where it is stored together with the orientation. Afterwards, the sensor is turned by 90 degrees clockwise. These two steps, measurement and rotation, are repeated depending on the number of points to be measured. We end up with a table of orientations and their corresponding measured angular rate values. We fit the data with a cosine function and the only free parameter is the phase. The offset is determined by averaging all obtained values and the amplitude is set to a fixed value. The fit employs a mean square error function with a golden ratio minimum search. The determined phase of the fit corresponds to the angle between the initial position and the north position. That is why finally the sensor is rotated by the amount of the determined phase in order to point to the north direction. The error of the fitting procedure is calculated from the formula shown in the bottom left. It decreases with the number of measurement points. Also, a higher signal-to-noise ratio improves the accuracy. By compensating the quadrature, the precision of the measured north direction can be improved by a factor of 6 to around 1 degree if the number of measurements and the measurement time is not changed. For longer measurement times, the precision is even higher. With this final photo of the gyrokompass, I want to finish my talk. I hope I could interest you in our MEMS gyroscope development and look forward to your questions. Thank you very much for your attention.